few core subjects like electrical machines, electrical power system. Okay, these are the core subjects of electrical engineering. Now, as far as the electrical power is concerned, so there are three phases of this power, electrical power. In one phase, the power is being generated. That is for the generation of electrical power. When in one phase, the power is transmitted and distributed. Okay, and at the end, the power is being utilized. Okay, so these are the three phases of electrical power. Now, we've seen that for electrical power generation, we need some electrical generators. Okay, for electrical power generation, we need generators, and the generators are discussed in electrical machine subjects. Okay, so there are different types of generator you have studied, like DC generators, AC generators like the alternators, induction generator may not be there in your curriculum. Other generators you have studied. And then the transmission and distribution, and that is the thing that you have studied under electrical power system classes. Okay, so like power system performance, power system planning and design. So these are the subjects in which you have studied the transmission and distribution part of electrical power. Now at the end, where the consumer is getting power after this distribution. So when the power is coming to the consumer, then how it will be utilized, that will be discussed in this subject. So it is called the power utilization, electrical power utilization. There are different types of application, as you can see in your household, starting from the electrical fan, refrigerator, air conditioner, light, and then heating, different types of heater you use in your households. So these are all comes under the electrical utilization. Not only as your household, at your household, in some other areas like electrical traction in railways. Railways is a bulk consumer of electricity. Okay, so these are all comes under the electrical utilization. But in this particular subject, you have two part. One part is electrical power utilization. Another part is electrical illumination. So illumination will be your illumination part will be taken by another teacher. You can consult the routine, class routine. Then you will get to know your class teacher. Now I will teach you that first part, that is electrical power utilization, in which we have uh, four chapters. First, we'll study that in case of non-linear load. So nowadays there are lots of non-linear loads in our common applications, common appliances. So due to this non-linear load, what kind of problem we may face at our end and also at the distribution end or the utility side. Okay, so that is the first chapter, uh, the problem due to the non-linear load at non-sinusoidal currents. In the second chapter is a big chapter where you study different means of electric heating, starting from resistance heating, induction heating, dielectric heating, etc., etc. So lots of electrical means of electrical heating you will study there. You will study there, and how to design electrical, how to do the electrical design for all these electrical heaters, and what are the merits demerits of different types of heating system. So that you will study in that chapter. So that is the chapter 2. In chapter 3 you will study the another thing is that is the electrical storage batteries. So storage batteries nowadays is a very important thing. Without that, we can't continue our daily life, because nowadays the electrical, the mobile phones are very much essential commodity for us. And not only mobile phone, our laptops and other devices which use the storage batteries. So storage batteries we have in the chapter 3. Now in the chapter 4 you have uh, uninterruptible power supply. That is another important application of electrical power utilization. Okay, so let's start the first chapter, which is the nonlinear loads and non-sinusoidal currents related issues. Am I audible clearly?
Yes,
Yes.
sir.
Uh, just a minute, let me open that whiteboard. Okay, it hasn't opened yet. Problems due to the non-linear loads. Okay, so can you define the non-linear loads? What kind of load we can say is a non-linear load? Hmm? Anybody? Non-linear load? Anybody? So you give us the example. Non-linear.
So a system like y is equal to alpha x, uh, which does not follow y is equal to alpha x, is a nonlinear system.
No, I'm asking the example. What type of loads behave like a nonlinear load.
So rectifiers, variable speed drives.
Carbon bulb.
Okay, so rectifier, correct. Rectifiers, variable speed drives, you can say
As
uh,
electronic devices.
like charger. The charger also consists of electronic parts, isn't it? And some device, some electrical device like a device having the saturation, magnetic saturation. That also we can take as a nonlinear load, isn't it? Okay. So let us take a simple example of rectifier. Okay. Bridge rectifier. Now in a bridge rectifier, I think we have drawn a lot of rectifier in power electronics class, isn't it? And here I have the load. Let us take a resistive load through which the load current is flowing. Okay. Now to call it a nonlinear load, we have to uh, see the characteristics of voltage versus current at the input. So therefore, you have to measure this current, the source current, and this is the source voltage. Okay. Now, if this is the circuit, this is the circuit of bridge rectifier. Everybody knows. Then what will be the output voltage waveform and output current waveform also? So if I try to draw all these waveforms in single graph. So suppose here I will draw the here I will draw the supply voltage. So that is the initial thing. And here I will draw the output voltage. And here I will draw the output current. That is IL. So what will be the source voltage in this case?
A
It's a
sinusoidal.
sinusoidal, isn't it? As we have used a alternating voltage source, so it will be a sinusoidal. Okay. Now, if I want to draw the output voltage waveform, how it will look like? Anybody?
Sir, it
Pulsating
will be
DC.
rectified. The pulsating DC, sir. The negative part will become positive.
Okay, so it's a full wave rectified waveform, isn't it?
Yes, sir. Full wave rectifier.
It's full wave rectified waveform, like this. Okay. Now, what will be the load current?
Sir, similar. means like a full. It will be a pulsating DC waveform.
Similar. That means okay. And what will be the source current?
So similar to the first source voltage.
Similar to the
Source voltage
similar to
means
the
VS.
source voltage. Have you analyzed whether it will be like source voltage or not? Okay, so let us take it's a source voltage. But in most of the application, we don't need this type of pulsating output current. We need a current which is ripple free DC. Ripple free. So we have lots of ripple in this voltage. So we need a ripple free voltage or a ripple free output current. So what should we do for that? Generally, what are the things, what are the measure we take generally for make the output current ripple free and output voltage ripple free? Anybody? This is very
Sir, we
easy
apply
question
a
from the
capacitor in parallel.
Filter, use of filter.
So capacitive filter in parallel
no
with the
no.
resistance load.
What does it do? If we connect some capacitive or some capacitance here, what will it do?
Sir, it will allow the AC component of the current to pass to enter, but it will pass on the DC component to
No, no.
enter through the
My
load.
object, you don't. No, no. Don't forget your objective. Our objective is to filter out the voltage and current ripple. So why I will use the capacitor? For which ripple? To eliminate which ripple I should use this capacitor? Got my question?
The voltage
So
ripple.
there are a ripple in both the voltage and currents.
The voltage ripple.
Whether this capacitor is enough to eliminate both the voltage and current ripples. If it is not, then which ripple will be eliminated by this capacitor? That is my
So
question.
by capacitor we eliminate the voltage ripple, and by inductor the current ripple.
Okay, so he's saying that we need one more element to eliminate the current ripple also. So that is an inductor. Okay, so an inductor is required to eliminate the current ripple. So that means the purpose of using this capacitor is to eliminate the voltage ripple. As capacitor doesn't change, it doesn't allow any change in voltage. So therefore capacitor will be used to filter out the ripple in the voltage waveform. And the inductor is used to eliminate the ripple in the current waveform. Okay, and if we use sufficiently large capacitor and sufficiently large inductor, then we can say that both the voltage and current will be ripple free, isn't it? Like this. So it's a ripple free. It's a ripple free current waveform. Okay. Am I right? So after installing the capacitor and inductor, we can have the ripple free voltage and ripple free current. Now, what about the other two waveforms? Whether they will change or they will remain same? That is the voltage and that input voltage and input current waveform. Anybody?
They won't change, sir.
The input current waveform will change, but the voltage.
Voltage will remain same.
Source cannot change because we are supplying.
Yes. Baro? Which will not change and which will change, or both the things will remain same?
Source voltage won't change.
Okay, source voltage won't change. So it will be as it is. And what about the source current?
So it will change. It will be like load current. It will be changed according to load.
Source current shouldn't change ideally.
No, it's not a source. It's not a current source. It's a voltage source.
Okay. Okay, so let us take, after installing this filter, our current becomes the 5 ampere DC, constant 5 ampere current. Okay. Now, as you can see, there are two halves. One is the positive half, another is the negative half of the supply voltage. Okay, so this is the positive half. Let us show by some red lines the positive half, and let us draw the current in that positive half. Now, can you tell me that which two diodes will be active or will be forward biased in that positive half cycle of the supply voltage?
D1 and D2.
So accordingly, only we have put the names, isn't it? So that means the current, and this you can say as a combination, the current will flow like this, and then it will return back to this. So this way, the current will flow. Okay. Now, you just tell me that at this positive half cycle of the supply voltage, what should be the value of IS? If
5
the
ampere.
load current, yes,
Sir, it should be equal
Paula?
to 5 ampere, the constant ripple free current during this period.
So it should be equals to, so if we use the KCL, Kirchhoff's current law, okay, so then you will get nothing but 5 ampere. Because if we apply KCL here, only IS current is entering, and here in the rest of the part, the IL current is outgoing. So IS is nothing but IL, and that is equals to 5 ampere. And in the negative half of the supply, the diodes which are forward bias are different. That is D3. The current enters from D3 and return backs from the D4. In this way, it flows. So this is the direction of current. This analysis already you have done in power electronic classes. Just a repetition. Okay. Now you just tell me that in the negative half cycle of that supply, what will be the value of IS?
-5, sir. If we take the direction into consideration.
Huh?
-5 ampere.
5 ampere only.
-5, -5.
No, what is that? So -5. Why -5?
Sir, because KCL IS is now
Because the direction becomes opposite. So if you take, this is the positive convention of IS. So in the positive half cycle, that these two direction matches. So therefore, it is positive 5 ampere. But in the negative half cycle of the supply, the direction is opposite. The assumed direction, assume positive convention for IS, and the actual current, that is opposite. So we have to write minus 5 ampere. And that is also ripple free. Okay. Now, can you tell me now that what should be the waveform of IS in case of ripple free DC?
It should be a square waveform if you're
The positive upside. Okay, so it's very easy that in the positive waveform it is 5 ampere, and in the negative waveform it is minus 5 ampere. So minus, okay. In this way we get a square waveform. Is this clear? But if you analyze the current in the similar way for the previous case when there was no filter, then whether you will get the same waveform. বুঝতে পারছো আমি কি বলছি? যখন ফিল্টার ছিল না, in that case, if we analyze the current, whether we'll get the sinusoidal current, you just uh, analyze once more.
So
Whether
resistance
the black waveform we have, সেটা একটু চেক করে নাও সেটা হচ্ছে কিনা। Got my point? I'm asking that when there was no filter, that case whether we'll get the sinusoidal output sound, sinusoidal source or a different source current.
So yes, for a resistive load, we will get the sinusoid.
No, load is resistive only, but without filter.
Yes, sir, will get sin.
Okay, so huh? Bolo? So that means we'll get in the positive half cycle we will get the similar, and in the negative half cycle it will be just opposite. We only with the negative sign 180 degree phase difference it will get. So we will get the sinusoidal waveform only. In this way you have to say that what type of waveform we should get for the source current. Not that just due to the just as the voltage waveform, the supply voltage waveform is sinusoidal, we'll get always this voltage sinusoidal. Here the current source current waveform depends on the load current. Okay, the source current waveform depends on the load current, not on the supply voltage. Okay, so the load current determines the source current. Okay, so that is one thing we have understood in this point, that without filter we was getting the similar nature of current as the voltage. So voltage and current waveforms are same. So though we are using some nonlinear devices like diode, but we can't say the total system is a nonlinear load, because the nature, two natures are same. The voltage and current nature remains the same. So though we are using four nonlinear devices like four diodes, but the circuit remains linear. Okay, but It is not the case when we are using the filters. When you are using the low pass filters, that LC filters, the thing becomes changed. And what we are getting? We are getting non-sinusoidal current, source current. Though the source voltage is sinusoidal, we are getting non-sinusoidal source current. So that means the waveform of the source voltage and source current are different. Then we have to call this circuit as a nonlinear load. Got my point? So this is an example. This is an example of nonlinear load. Where though you are using sinusoidal voltage, but we are not getting the sinusoidal current. The waveform differs from its sinusoidal nature. Now, when a waveform is not a sinusoidal waveform, other than a sinusoidal waveform, what we can do for it? Anybody?
So harmonic analysis.
Harmonic analysis. Why? Is saying that if we have a non-sinusoidal waveform, we have to go for harmonic analysis. Why? Why so? কি হলো? বলো।
Nonlinear periodic waveform can be Fourierly analyzed by breaking it into sinusoidals by Fourier analysis.
Now, why we'll go for this Fourier series and we have to get the sinusoidal things?
Sir, because only the fundamental component of a current or voltage is responsible for the power delivery. That's why we need to we need to calculate the fundamental waveform, fundamental component.
Then what about the rest? What about the residual?
Sir, rest are not responsible for the active power.
But then what will বাকিগুলো কি কাজ করবে তাদের? পাওয়ার না দিল না কিন্তু সেগুলো কি করবে? মানে whether those will be required, whether those components will be required or not. Harmonic analysis not doesn't mean then only to find out the fundamental. Harmonic analysis means you have to find out the fundamental plus all the harmonics, or at least the dominant harmonics. That is meant by harmonic analysis. If you don't need the harmonics, you just use a filter, okay, having your central frequency of your fundamental frequency and filter out your fundamental waveform. You don't need harmonic analysis. Okay, so the harmonic analysis is basically is done based on the Fourier series, isn't it? Now,
Yes, sir.
what is the Fourier series? What does it say? Fourier series says that a non-sinusoidal periodic waveform can be expressed, can be represented as a summation of infinite number of weighted sinusoids. Okay, as a summation of infinite number of weighted sinusoids. Not only fundamental, there should be infinite number of sinusoidals, and their weights will be different. Their weight means nothing but amplitude. Their amplitudes will be different, isn't it? So that you have studied lot of times, like in mathematics, in signal systems. Okay, so you have studied the Fourier series. Clear? Now, what are the harmonics?
Multiple of fundamental frequency.
Harmonics, but fundamental, I don't know what is the fundamental frequency. I have only the non-sinusoidal waveform. If I don't know harmonics, then how can I know the fundamental? Okay. So what is fundamental? You just define that, then you can say that this is that integer multiple of the fundamental is the harmonic. Huh?
Same frequency as that of the non-sinusoidal waveform will be the fundamental frequency.
Correct, correct. Fundamental frequency is the frequency of the original wave, and the harmonics will have the frequency that is integer multiple of the original wave. Original non-sinusoidal waveform is basically a periodic waveform. It will give you some time period. It will give you some frequency. That is called the fundamental frequency. Okay, and the other harmonics, that should be the integer multiple of the original waveform's frequency. Okay, so if the original waveform has 50 hertz, then the harmonics would have 100 hertz, 150 hertz, 200 hertz, 250 hertz. We won't get any 99 hertz or 125 hertz or 180 hertz or 260 hertz. So this type of frequency will not occur. You will get the discrete frequencies. You will not get all the frequencies in case of Fourier series. You may get that in case of Fourier transform. But for Fourier series, you will get only the discrete frequencies. Okay. And these frequencies will be integer multiple of the original frequency. Clear? So that this basic background of Fourier series you should have. Okay. So that means it is clear that we have to go for harmonic analysis. Then my question have not been answered yet, that why we will go for this Fourier series or harmonic analysis. Okay, so we will get some sinusoidals like fundamental, higher harmonics, etc. But what is our objective? Why we'll go for this Fourier series or analysis?
We can use eigenvalue, eigenvectors in mathematics will be very easy.
No,
Sir, phasor analysis will be done
that
only through sinusoidal waveforms.
Because most of the machines are designed for pure sinusoidal waveforms. So if there are harmonics, then there will be humming noise, and the RMS value of the waveform may also increase. So there can be increased heating, which may damage the insulation. So in order to know
No,
this,
no.
we have to go.
If the machine is based on sinusoidal waveform, and then you have this non-sinusoidal waveform, and after the Fourier series, after the harmonic analysis, also you will have this non-sinusoidal waveform only. That
Yes, sir.
means some
But
fundamental plus
we
some
can
harmonic.
design filters according to that. After doing the harmonic analysis, we can decide the bandwidth of the filter.
Filter. Have you seen any filter used with electrical machines like motors, transformers, etc.? Have you seen any kind of filters? Filters are used mostly for small circuits like digital circuit, analog circuits, etc. But have you seen any filter? Because you know that transformer generates harmonics that you have studied in three-phase transformer.
Yes,
But
sir.
have you seen any filter used with transformers? Or every generators that due to its nature of the flux distribution, generators also contain some harmonics in its voltage waveform. So have you seen any filter used with generator?
No, sir.
Then
Sir, from
okay.
the
Now actually, follow.
sir, from the fundamental, we can find out the fundamental power factor, and that will help us in calculating the supply power.
Okay. So let me answer like this. Suppose we have a sinusoidal, a non-sinusoidal waveform. Okay. But if we have the if we have splitted that non-sinusoidal waveform, and if you could get the a series of sinusoidal waveform having different frequencies, at least we are getting some sinusoidal waveforms. That is the first point. Okay, সেটা তো নন সাইনুসয়েডাল তো আর থাকছে না, সেটাকে স্প্লিট করে আমরা অ্যাটলিস্ট কতগুলো সাইনুসয়েডাল তো পাচ্ছি। And for sinusoidal thing we have a developed mathematics that is called the phasor algebra. And that from phasor algebra we can find out the reactance which is based on the sinusoidal assumption. If we get the reactance for fundamental, the reactance for other harmonics will be different. But we can define some reactance for third harmonics as well, isn't it? But we cannot define any reactance for a square waveform, for a non-sinusoidal waveform. Okay, so at least if we go for the Fourier series or harmonic analysis, then we uh, could have lots of sinusoidals having different frequencies, and we can also use our existing mathematics which is called the phasor algebra for them individually. For fundamental we can use some mathematics, existing mathematics. For third harmonics we can do so, for fifth harmonic we can do so. Okay, so that is up to us, that up to which harmonics we should consider. Clear? And by this sinusoidal thing we can analyze the effect of the harmonics on the performance of the device. Like if it is a motor, then how this harmonics, how this other sinusoidal will behave. So if we have the sinusoidal, then only we can analyze the performance, because sinusoidal waveform, sinusoidal things are very easy for calculations, isn't it? জিনিসটা যদি একবার সাইনুসয়েডালে বেরিয়ে যায় তাহলে আমরা তার মানে ডিভাইসটার পারফরমেন্সটাকে অ্যানালাইজ করতে পারবো। তো এইটা একটা অবজেক্টিভ, বুঝতে পারলে? সেই জন্য আমরা এটা একটা হারমোনিক অ্যানালিসিস করতে পারি। So we have seen that can you tell me that what are the harmonics will be there in particular waveform? Or you have to calculate?
Odd
Odd
harmonics.
harmonics will be
First you
present.
tell me that
Odd and fundamental.
huh?
Odd harmonics.
Odd and fundamental,
Fundamental
even in
and
this
Odd
odd, odd.
harmonics.
odd harmonics. All the odd harmonics will present.
Except third harmonics.
Third harmonics will
Sir,
not present.
sine is the sir sine curves of odd harmonics.
Forward গুলোই থাকে।
Sir,
Those or
3n,
harmonics
6n
are
minus
sine
1,
waves.
6n plus 1.
বুঝতে পারলাম না, এত নয়েজ আসছে আমি কিছু বুঝতে পারছি না, কিছু বুঝতে পারলাম না, কি বললে?
So
Odd
third
harmonics
harmonics,
means the third, fifth, seventh, ninth এইগুলোকে তো odd harmonics বলে যায়। তো এগুলো থাকবে কি থাকবে না?
Half wave symmetry আছে।
Okay, so হ্যাঁ, তাতে কি এগুলো কোনগুলো থাকবে না বলো?
3K harmonics গুলো।
Okay, so better you you go for this Fourier series and find out that will be your home task. Okay, so what is the exact contents of this particular square waveform? You have to find out with their weights, corresponding weights of third harmonic, weights of fifth harmonic, weights of fundamental, etc. First, you have to find out those. Okay, now the rest of the chapter will be discussed with the issues due to this harmonic in the source current. So that means one thing is clear, that if we have a nonlinear load like the load we have taken in that example, so if we have this kind of nonlinear load which are very much present in our modern appliances, because most of our modern appliances have some power electronic circuits, starting from your charger or mobile phones, charger of mobile phones, charger of uh, laptops, okay, that smps you are using for pc, okay, ups, etc, etc. So there are lots of gadgets, lots of device we use for our uh, household applications. Most of the device contains some power electronic circuits. So that means there is a possibility of nonlinear loads in most of the appliances we are using nowadays. Okay, so if it is so, then uh, we can expect that there will be lots of harmonics present in the source current. Okay, so that means as a consumer, we are basically injecting the harmonics into the source current, because here the utility is not coming to inject the harmonics in the source current. We have assumed that utility is giving you perfectly sinusoidal voltage source, but you are the person who is inserting you are inserting that harmonics into the line current. Okay, and if the harmonics are present in the line current, what kind of problem we may face, that we should discuss in details, because till today we have discussed everything based on the sinusoidal assumption, starting from your machine design, starting from your any kind of design and analysis. We have assumed that voltage will be sinusoidal, current will be sinusoidal, power will be there. There is an apparent power which has two components, reactive power and active power. So these are all based on our assumption that voltage and currents are sinusoidal. But if they are not sinusoidal, what kind of problem we may face? Truly speaking, that till today it is not possible to explain all the things happen due to the harmonics. Till today there is no design tool which uh, take the harmonics into the consideration during design phase. Okay, so that means whatever the problems occurs due to this harmonics, sometimes it's called ghost problem. There is no actually explanation for those. We cannot explain those. Okay, so a few problem uh, we'll discuss here. So those are the problems due to the harmonics. So let me write the list first, and we'll discuss in the next class. So the problems harmonics present in the line current. Okay, so number one, reduction in power factor. Number two, distortion in bus voltage. Okay. Number three, uh, problems, because it's a long list. So I have two problems related to line equipment. তো লাইন ইকুইপমেন্ট বলতে অনেক কিছু বোঝায়, সেই জন্য একসাথে হয়ে যাবে লাইন ইকুইপমেন্টস। Problems. So there are other divisions in the point 3 and point 4. So problem related to measuring instruments and circuit breakers. Okay, so these are the major categories, but there are subcategory obviously, uh, mainly in point 3 and 4. So that I will discuss in the next class. Okay, so these are the problems related with the power systems only. There are other problems as well, but that is out of scope. Okay, so if you have any question, you can ask. whatever we have discussed today. On that, if you have any question, you can ask. Okay. Now, one thing I should mention here that you know that what is THD, total harmonic distortion. Have you heard the term?
Sir, just heard it, don't know what it is.
We have just heard it. Okay. So that total harmonic distortion means how much percentage of harmonics present in that waveform. Okay. So to know that how much harmonic is present, what you have to do, if we have the total current, like suppose total current you have, then how we can find out? Just I'm just asking that if we have the total current, suppose IS, and you know the fundamental part of it, I1, that then how you can calculate that distortion? How you can measure? How can make a measure for total harmonic distortion?
RMS square minus average square.
Mhm. How will find out this IH? Okay. This is called the total harmonic distortion. Okay, with respect to the fundamental harm, what is the uh, total harmonic content in that current, in that source current, or it can also be measured for voltage. So there is a certain limitation imposed by this different standard. Like in our IES, we don't have any standard for THD so far I know, but in IEC standard they have some limit. They have some guidelines for THD, and that is for current it should be less than 10%. I think that standard is IEC 512. I have to check once again, but I think it is IEC 1.1512. According to that, your appliance which you are using should have THDI less than 10% and THDV we should be less than 5%. Have to check exact percentage. So some guidelines are there uh, by this IEC standard only, but there is no guideline for our Indian standard IS. But this THD is very much important term nowadays in most of the uh, advanced electronic appliances. They mention the THD in their nameplate. Okay. Any question? Okay, so let me take the attendance then. Attendance, I will just record it because the total the lecture is being recorded. We have started with 56, now it becomes 51. স্পন্দন সেন চৌধুরী, শুভদীপ ভট্টাচার্য, শুভময় বিশ্বাস, সুব্রত মাহাতো, সুগত বিশ্বাস, স্বাতি সাই. You people didn't rename yourself. So as I told you that you should rename yourself properly. Okay, so from the next class, you just try to rename yourself at the beginning. So anyway,